So I'm just realizing that I was probably muted, so I'm sorry about that. But you did see what I was doing here. So this undefined slope is the x equals some number, which is a vertical line that has the undefined slope. So once you have this situation, you realize that it's the 2 here that you care about, because it's x is equal to the number that's in the x part of the point. So the equation of the line is going to be x is equal to 2. And on the other side here, where a line that has a slope of 0, this one is y is equal to some number, which has a horizontal line for its picture and has a slope of 0. So this one is going to be y is equal to -1. Okay. So write an equation of a line that's passing through the point -8, 3 that satisfies the given condition. Give the final answers in slope-intercept form. So we want this line to be parallel to this line. Okay. So in order to be parallel to this line, it has to have the exact same slope. So the slope of this line is going to be the opposite of A over B, which is going to be 2/3. Okay. And if it's going to be in slope-intercept form, you want y equals mx plus b, and you already know what the slope is. The slope is going to be 2/3 x plus b. So the only thing that we don't know right now is our b. That's the piece to this. We're like halfway there to getting our equation in slope-intercept form. All we have to do is figure out where this thing crosses the y-axis. So I'm going to use this point here that they gave us because it's got to pass through this point, which has an x and a y. And conveniently enough, in this form, there's an x here and a y here. So we can just substitute these values into our equation here. So this is going to be 3 in for y, 2/3 -8 plus b. And what we've done by substituting our x and y is we've created an equation with one unknown that we can use the techniques that we learned in chapter 1 to solve for b here. So we have a fraction. I'm going to get rid of that fraction. That's just the path of least resistance for me. I'm going to multiply everything by 3. So that's going to be 9 is equal to 2 times -8 plus 3b. So 9 is equal to -16 plus 3b. Add 16 to both sides, you get 25 is equal to 3b, and b is equal to 25/3. And this is the nasty y-intercept that you eventually would have to graph to the best of your ability. Obviously, it's hard to know exactly where this is unless your grade goes up by thirds, but you would just do the best that you can. So y is equal to 2/3 x plus 25/3. This is an equation in slope-intercept form. All right, so suppose that there's a flat rate of 20 cents plus a charge of 10 cents per minute to make a telephone call. Write an equation that gives you the cost y for a call of x minutes. So again, this is one of those situations where there's a flat fee just to take the thing to start the phone call, and then 10 cents a minute. Or if you were like renting a snowmobile out in the wintertime, and they say, all right, it's $100 to rent the snowmobile plus $20 an hour for however long you have it out there. So for the longer you have the snowmobile, obviously the more expensive your cost is going to be, right? So we have some cost that they said is y, and that's going to be equal to our 10 cents per minute plus the 20-cent flat fee. So there's your equation for a cost of x minutes. All right, so use the ordered pairs here to find an equation that models this data. Okay, so obviously this isn't 100% linear, but what we can do is kind of take this year right here and this year right here to use that as a linear model for the growth. Okay, again, this isn't exactly linear, but we can try to project it as a linear growth if we select 2 of the years. Okay, so we do 262 minus 255 over 11 minus 9, and that will give us 7 over 2. And there is our slope. So y equals 7/2 x plus b. And what we should do now is figure out, what we can do with one of these points. So I'm going to just, again, select one of these points, probably this guy right here. So we'll do 255 is equal to 7/2 times 9 plus b. And if you wanted to, you could multiply by 2 to get rid of your fraction. It would just make your life a little bit easier. So we'll do that. So this is going to be 5/10 is equal to 7 times 9, because the 2's will cancel. It gives us 63 plus 2b. And then we'll subtract 63 to both sides here. And that will give us 447 is equal to 2b. And then we will divide both sides by 2. So our final equation that models this data will be y equals 7/2 x plus 447 halves. All right, so 2.4 linear inequalities in 2 variables. So linear inequalities are graphed almost the exact same way as linear equations. Their pictures are very different because there's some shading involved. Because again, it's not just the points that satisfy the equation, it's the points that satisfy the inequality that we're going to be looking for. So it's going to be a lot more to it than just the line itself. The line ends up being sort of like the boundary of your solution set versus being the solution set when it was an equation. Okay, so again, there are 4 different variations, because you have the less than or equal to, greater than, and greater than or equal to. These are standard form of linear inequalities in 2 variables, very similar to the linear equations in 2 variables. Okay, standard form. So over here, this talks about the line x plus y equals 5. So this is the line that is x plus y equals 5 right there. And that would be the line if it was an equation. The second you start talking about an inequality, it is no longer just this line anymore. It's all of the points that will satisfy this inequality of saying if you add up the x and y coordinates, they're going to be greater than 5. And they've selected a couple of points over here, 2, 4, 2 plus 4 is 6, which is greater than 5. So this is part of the solution set. 5 plus 3 is 8, which is greater than 5. So this is part of the solution set. So all of these points here on this side of the line satisfy the inequality of x plus y is greater than 5. Okay? And on the flip side, these are all of the points that satisfy the inequality that is less than 5. All the points over here on this side are all of the points that are going to satisfy the inequality of x plus y is less than 5. So to graph these linear inequalities, you draw the graph of the straight line as the boundary. It's a solid line if it's less than or equal to or greater than or equal to. It is going to be a dashed line if it's a strictly less than or strictly greater than. Basically saying the line is either part of the solution set over here, or it is not part of the solution set. Sort of the idea of like using the square bracket or the parenthesis when we had just a single variable. All right, so think of the similarities between those ideas when you're doing the inequalities in 2 variables. Okay, choose a test point. Usually 0, 0 is a good test point. The only time you can't use 0, 0 is when your line actually passes through that point. You'll have to select a different point that is not on the line because you want to figure out which side of the line you're supposed to be shading. Okay, so 0, 0, again, is a good test point to use. Step 3, shade the appropriate region. Shade the region that includes the test point if it satisfies the inequality. Otherwise, shade the region on the other side of the boundary line. All right, so let's take a look at this guy. So right away, we know that this is going to be a solid line. So I'm just going to put that here as a reminder that it's less than or equal to. So I'm going to use the solid line, which means the line is going to be part of my solution set. Okay, so I'm going to graph this. It's in standard form, so maybe I'll use my intercept table of 0, 0. So if you substitute 0 in for x, you figure out that y is 4. And then if you substitute 0 in for y, you figure out that x is 4. So you have the 2 points, 0, 4, and 4, 0. So those are our 2 points. Again, it is a solid line, so I'll go ahead and I will connect those dots with a solid line. And then the next thing I'm going to do is I'm going to use my test point of 0, 0. And I'm actually going to put the test point here on the grid so I can see exactly which side of this line I will eventually be shading. And then you substitute the test point into the original inequality. So 0 plus 0 is less than or equal to 4. Is 0 less than or equal to 4? Yes or no? And the answer, of course, is yes. So this is a true statement, which means if this test point is true, every single point on this side of the line is also going to be true. So this is the side of the line that I'm going to shade. And you don't have to be, precise with it. Just let me know that this is the side of the line that you are meaning to shade. Okay. So let's do this one now. So again, standard form, we have 0 over here, which means this is going to pass through 0, 0. So you can't just use your standard x, y, 0, 0 because you're getting the same point twice. So let's kind of abandon ship on this guy. And then what I'm going to do is I'm going to turn this into slope-intercept form. So I'm going to say y is greater than negative x because I'm going to subtract x to both sides of the inequality. So this is in slope-intercept form where your slope is -1 and your intercept, of course, is 0. We already talked about that. So our intercept is 0, 0, our y-intercept, and then our slope is -1, so down 1 over 1. Remember, it's a negative slope, so it should be going down from left to right. So down 1 to the right 1. Again, you could also go up 1 to the left, up 1 to the left. And since this is strictly greater than, this is going to be a dashed line. So I'm going to do my best to put in a dashed line here. Boom, 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 boom. There we go. And of course, I need my test point now that my boundary line is graphed. So my test point, and I cannot use 0, 0 because my boundary line is passing through that point. So I'll pick some other point. I'll pick 1, 1. 1, 1 is hanging out over there, so I'll try it. So 1 plus 1 is greater than 0. That looks like 6. Is 2 greater than 0? That is a true statement, which means every single point on this side of that line is going to be true as well. So I just shade all that and I move on. Do one more of these. So probably a few more. So y is going to be less than or equal to -4. So again, I want to get my y by itself if I can, since my x is not there. And this is the same situation that we had before where your x was gone. So this is going to be a horizontal line at -4, and it is going to be solid because it is less than or equal to. So I'm going to put -4 here. It's a horizontal solid line. So throw that in there. And it says that y is less than or equal to -4. Now these horizontal and vertical lines are actually pretty easy to figure out which side you need to shade. So you don't necessarily have to use the test point. You can if you wanted to, but you don't have to because you know what values for y are less than -4. It's all of these values down here. So this is the side of the line that you're going to shade. Again, you could do a test point if you wanted to by saying, all right, I'll substitute 0 in and see what happens. So 0 plus 4 is less than or equal to 0. Is 4 less than or equal to 0? No, of course not. It's false. So since it's on this side of the line and it gave you a false statement, we shade everything on the other side of the line, okay? All right, so now we're going to be graphing these linear inequalities with and or. Remember, and represents the intersection, where or represents the union. So you would be putting both together if it was an or problem. So I'm going to graph this one, and then I'm going to graph this one, and I'm going to figure out where their shaded regions overlap. Because remember, with and, we're looking for the intersection of the shaded regions. Just like we did with a single variable, we looked for the intersection of the shaded regions of when we had just the line. Well, now we're going to have a Cartesian plane that we're going to be graphing these two variable inequalities on, and we're still going to be looking for the overlapping of the shaded regions, okay? So let me go ahead and graph this one. We can use our intercept table here pretty efficiently. So substitute 0 in for x, you get -4 for y. Substitute 0 in for y, you get 4 for x. So you have one of them is here and the other point is there, and it is a solid line. So I will connect those now. Okay. And test point 0, 0. So let's go ahead and substitute that in to see if it's true. Is 0 minus 0 less than or equal to 4? Is that a true statement? You're darn right it is. So I'm going to shade everything on this side of that line, okay? Over here, this equation is going to be x is greater than or equal to -2. So I'm going to see if I can pull in another color here to see if I can graph that one in a different color. So this is going to be x is greater than or equal to -2. And again, it's a solid line. So there's that one. That one's a vertical line. So x is greater than or equal to -2. And again, you know what values for x are greater than or equal to -2. It's all of these values over here. So you start shading everything over here on this side of that line. And now we care about where the shaded regions overlap each other. So what I'm going to do now is pull in one more color here to see if I can highlight exactly where the shaded regions overlap. So the shaded regions overlap in this black here. You can see it right here, and everything in between. So this is the shaded region of where the shaded regions overlap each other. And this is the solution set. All of these points that are within these this black shaded region is the solution set, okay? So all of this stuff that's shaded over here doesn't count. All of this stuff that's shaded over here doesn't count because we only care about where the shaded regions overlap, and because this is an and problem, okay? So let's do this one, see how this is gonna turn out. So we've got x, y, 0, 0. I'm gonna just do this one. So when you substitute 0 in for x, you get -7 for y. When you substitute 0 in for y, you get +3 for x. So let's graph these points. So there's that one, and here is this one, and it's strictly less than, so it's going to be a dashed line. So I'm gonna do my best, put in a dashed line. There we go, There we go. And test point of 0, 0, right there. So let's do 7 times 0 minus 3 times 0 is less than 21. So is 0 less than 21? That is a true statement. So I'm going to shade everything on this side of that line. So everything here is getting shaded on this side. Okay? Change colors. Let's go back to red for this one. Again, it's a dashed line because it's strictly greater than, and this is a vertical line again. So vertical line, dashed, put your arrows in, and it's all the stuff that's greater than. So I'm going to shade everything here on this side right there. And because this one is an OR problem, so let me just swap out my colors one more time. This right here, since this is an OR problem, we are going to take anything that is shaded and say it is part of our solution set. So basically, it's everything except here. It's everything except this region, which has absolutely no shaded stuff going on. It's everything that's over here. It's everything where it's overlapping, and it's everything where it's just black, because it doesn't matter where it overlaps here, because this is not an AND problem. It is, if it's shaded, it's part of the solution set. So it's everything over here. I'm just going to go nuts. Shade, 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 shade. There we go. There we go. And we just want to make sure that we highlight this region that is our boundary. So this is our boundary right here of where we are going to stop our shaded region. So we just highlight that to say everything up here is shaded, nice, nice. It's part of the solution set. Anything that's in this region over here is not going to be part of the solution set. All right. So 2.5, we're going to talk about the introduction to relations and functions. Functions are a big part of algebra and beyond, if you start getting into calculus and things like that, for those of you who are going to continue. So we're going to talk about these two important concepts in this section. So a relation is a set of ordered pairs. So we have learned what a set is in this course so far. We know that they are, denoted with these curly brackets, and it's a bunch of ordered pairs. So it's a set of ordered pairs. So maybe something like this. This right here is a relation. It's a set because it has the curly brackets. There's two ordered pairs in there. So it's a set of ordered pairs. Very small relation, but it's a relation. It's satisfying this definition. Okay, so we are going to take this relation over here and we're going to write it as a set of ordered pairs. All right, so we need the curly brackets. We have -4, 0. We have 0, -2. We have 3, 1. We have 5, 1. And one thing that you want to keep in mind here is that in sets, you have no repetition. So for whatever reason, if they put in another line here and said, oh yeah, there's this other point that says 0, -2, you would not repeat this point in that set. You wouldn't do it. There's no repetition in sets. What I usually show students when I'm teaching a class that specifically has sets as part of the course is I usually show them this set right here. So A, L, G, E, B, R, and then I close the set. And students get it. They're like, well, some of them go, well, you forgot the other A, right? This is the set of letters that spell the word algebra. But I do not put comma A here because A is already in the set. There is no need to repeat it. Matter of fact, it's not just no need to repeat it. You should not repeat it. There's no repetition within that set. So a function is a relation, which means it is also a set of ordered pairs. For each distinct value of the first component of the ordered pairs, there's exactly one value of the second component. So we say that a function is 1 to 1, which means the x values do not repeat. If the x value is repeating, it's because it is going to 2 or 3 or 4 different y values. So there's only supposed to be exactly one value for the second component for every single one of those first components. So if you have this, again, a set of ordered pairs, you have 1, 5, and then you have 1, 7. This is still a relation. It's still a set of ordered pairs, but it is not a function because the x values are going to 2 different y values, all right? And you're only supposed to have exactly one value, okay? So we're going to determine whether this is a function. So 0, really all I'm looking at are the x values. So I see 0, -1, -1. This is no, it's not a function. This is 5, 6, and 7. I don't care that the y values are repeating. That doesn't mean anything to us. This is a function. So relations may be defined in several ways. We've seen a set of ordered pairs denoted with the curly brackets. We've seen them written in table form. They can be defined graphically. They can be defined by a mapping. So a table, again, we saw that before. We can create an equation. A linear equation is going to be able to define a function. And a mapping, for those of you who have never seen one or can't remember what they look like, it would be something like this. So if you had, a oval with the x up top, and then you had another oval over here with the y's, and let's say you had a couple of values here. So let's say you had 5, 7, and 10 over here. And let's say we had 0, 1, 2, and I don't know, 3, something like that. So 3. And a mapping would be if you went from 5 to 0, that is the point 5, 0. Then you went 7, 1. That's the point 7, 1. And then if you went 10, 2, you would have 10, 2. And then if you had 10, 3, this would be 10, 3, which means this would not be a function because the x values are repeating. It's still a relation. It's still a set of ordered pairs. So I've just got to put the curly brackets in here. It's a set of ordered pairs, but it is not a function because it is not satisfying the one-to-one relationship. Okay. So for every relation defined as a set of ordered pairs, x, y, there are 2 important set elements. You have the x values, which are your domain, and you have the y values, which are your range. This is a concept that seems to come back quite a bit throughout this course. It goes away, and then it comes back again, and goes away, and then comes back again. So it's something that's worth remembering, worth studying, so that way you don't have to constantly go back to this video to try and remember what the domain and range actually are. The way that I remembered which one was which was x comes before y in the alphabet, d comes before r in the alphabet, so the x went to the domain and the y went to the range. That was just the way that I remembered it. You're going to have to find a way that works for you. Okay? So give the domain and range of the relation represented by the table below, and does it define a function? So these guys right here, the first ones, is our domain, and this is our range. The range is also known, the y values are also known as your dependent variable, where x is your independent variable. So your y's will depend on, so your cost depends on how many gallons you purchase. Obviously, it also depends on how expensive the gallons are, but the biggest cost is the number of gallons that you purchase, okay? So if you obviously buy no gallons of gas, it will cost you no dollars. Looks like it's $3.50 a gallon. This is pre-COVID. I just saw in Rhode Island, it was like $1.59. That's pretty sweet for regular gas, okay? So this is our X, this is our domain right here, and this is our range. And one of the things that you want to really understand too is that the domain is the set of values in the for the X values. So the domain is actually a set in its own right, which is 0, 1, 2, 3, and 4. And your range is also a set, which is 0, 350, 7, 1050, and 14. So it's also a set as well, okay? And it does define a function because none of these X values are repeating. It's not like, you know, I bought two gallons of gas and it cost me $7, and the person right next door to me, next pump over, bought 5 gallons of gas and it also cost them $7. I wouldn't be very happy paying $7 for my 2 gallons when they got the way more gallons of gas for the same price. Okay? That would not be a function if they were selling the gas for the same amount of money if you were getting different amounts of gallons. Okay. So we're going to give the domain and range of this relation. And we're also going to do a spoiler as well to figure out if this is a function, okay? So the domain is the set of X values. So the set of X values, I'm looking at this, it looks like it's going to continue on forever in this direction. It's going to continue on forever in that direction. So the domain here is going to be all real numbers. And if you remember how we represent that, we can use an integral. So this is from negative infinity to positive infinity. There is your domain. It is your set of X values, your possible X values. Not just what you can see, what is possible within this graph, okay? Your range has a maximum height. This height, this Y values are never going to get larger than 4. It's going up to 4 and then it gets shot right back down. So, but it does go down to negative infinity. So negative infinity is where this thing is heading and as its minimum value. And it has a maximum value of 4 and it appears that it actually gets there. So there's your domain and range for this picture. And we are going to figure out if this thing is a function or not, okay? FNC is the abbreviation function. And we can use something that's called the vertical line test to figure out if it is a function. Remember, the X values cannot repeat. So if the X values are repeating, it would fail the vertical line test, which means it would touch the picture more than once. So I put a vertical line in and it only touches my picture once. I put a vertical line in and it only touches my picture once. I put a vertical line in, only touches my picture once. This is passing the vertical line test, which means the X values are not repeating. So this is a function. All right, so now they're showing you the vertical line test right here. Again, they're showing you if you drew a vertical line into this picture, it would touch here and it would touch here, which means it is failing the vertical line test. So this is not a function. It's a relation, it's a set of ordered pairs, but it is not a function. This is a function. The X values are not repeating. Okay, so we already did this, which is why I just skipped over it very quickly. Okay, if a relation is defined by an equation involving a fraction or a radical, apply these guidelines when finding the domain. Exclude from the domain any values that make the denominator of the fraction equal to 0. Okay, so you're going to have to be setting these denominators equal to 0 if there are variables down there to figure out what is not in the domain. And exclude from the domain any values that result in an even root of a negative number. So we don't know how to take the square root of negative 10 because we don't know how to deal with imaginary numbers yet, complex numbers. We will later on in this course, but for now, we do not know how to deal with those. Okay, so let's figure out if this defines a function, okay? And then we'll give the domain. So this is a linear equation. If you remember sort of vaguely what this looks like, this has a negative slope. So this probably looks a little bit like that. I'm just trying to visualize what this picture is going to look like. And if this is what my picture looks like, it doesn't look like it's going to fail the vertical line test. The only one that would fail the vertical line test is this equation, right? X equals 5 would fail the vertical line test pretty miserably because this is the equation of a vertical line at 5. So this would fail the vertical line test. But this one looks like it's totally fine, only touches once, only touches once, only touches once. So this is a function, definitely. And if I'm looking at this, I also know that the domain is going to be all real numbers. Most functions have a domain of all real numbers. Again, there's only a couple that have some restrictions. You know, if you have x's in the denominator, if you have even roots, you know, square root, the 4th root, the 10th root, something like that, you have to be a little bit suspicious of values that are going to be causing some problems with your graph. Okay, so over here, this is a square root. So again, we have to figure out what values are going to make this negative, right? Because we don't want those. So the quick, slick way to do this is to take whatever's in this radical, okay, into the square root, this 5x minus 6, and we set it greater than or equal to 0, because that's your boundary to positive and negative numbers, right? Remember, it says we don't want anything to be negative inside here. So how do we make sure that it's not negative? We make sure that it is greater than or equal to 0, because these are the values that are positive. And then we solve for x. So we're going to add 6, you get 5x is greater than or equal to 6. You get x is greater than or equal to 6/5. So these are the values that x can be. These are the values that x can be. So we know what the domain is. The domain is going to be values that start, it's greater than or equal to, so I'm going to use a square bracket. It's going to be from 6/5, and then it's going to head all the way to infinity. This is a function. There's no way that the x values are going to give you, have any repetition. If I plug in a 5 here, I'm not going to get 2 different numbers for y. I'm just going to get whatever the value is. I'm going to get the principal root. All right. This guy over here, this is actually a problem for us. This is going to lead to not being a function, and I'll explain why this is not a function in a minute. And then this one over here is also not a function. And this one's a little bit quicker to explain why this is not a function, and it has everything to do with that shaded region. So you have a 4x plus 2, it's in slope-intercept form of a linear inequality. So it looks like this because it's got like a positive slope, right? Again, ignore that that's a little bit crooked. And then there's some shading going on. I don't know if it's, you know, here or there. I'm just sketching this. So I know that there's usually some shading involved with these inequalities. And if there's shading involved, if I try to put a vertical line in here, it touches my graph here, but it also touches here, and 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 here. So it is failing the vertical line test miserably. It is like miserably failing the vertical line test because that shaded region has a, you know, infinitely many points in there that are touching a vertical line, and we're only supposed to have one in order for it to be a function. This one, when we take the 4th root, we get positive and negative versions for x, and that's why we end up not having the function here, because you would have to take the cube root of both sides, and that's what's going to lead this to not being a function. For every x value, you're going to get multiple y values, and that's no good for us, because remember, you're only supposed to get one y value. And then down here with this fraction, again, you just set the denominator equal to 0. Because you have an x down here, we want it to be equal to 0 so that way we can figure out what values are not going to be in the domain. It's sort of the process of elimination. We know that the domain is usually all real numbers, but sometimes we have to take some out. Okay, in this case, we're going to figure out what values are going to force this denominator to be 0, which makes it undefined, which means we can't have it. So that's 5 plus 3x is equal to 0. 3x is equal to negative 5. X is equal to negative 5/3. So this says if x is equal to negative 5/3, then the denominator is 0. So we are saying that x cannot be equal to negative 5/3, because if it were, then it would make my denominator 0. Okay, so the domain is going to be, so our domain is going to be all real numbers except for this. So the way that we do that without having to write all those words out, so we say x such that x is not equal to negative 5/3. Okay? So variations of the definition of a function. A function is a relation in which for each distinct value of the first component of the ordered pairs, there's exactly one value of the second component. A function is a set of distinct ordered pairs in which no first component is repeated. A function is a correspondence, mapping, or an equation that assigns exactly one range value to each distinct domain value. And there we go. And I believe this is the last section of this chapter, which is function notation and linear functions. Okay, so function notation is just a fancy way for us to write y. Not really. It's kind of the running joke that I say in my classes. It's just a different way of representing y. There's lots of reasons why we use function notation. I won't bore you with all those. I usually bore my students with it, but given the fact that this is a digital course, I will refrain from doing it. So f of x is just another name for the dependent variable for y. All right. So what we do here with these f of x, and this is usually not the way that we represent this, and I'll show you in 1 second what we do, is this says f of x is equal to 6x minus 2, which means y is equal to 6x minus 2, and we want to figure out what the value for y is if we substitute in negative 3. So we are going to say y is equal to 6 times negative 3 minus 2. So y is equal to negative 20. Negative 18 minus 2 is negative 20. So this says that when x is negative 3, the one and only y value is going to be negative 20. Okay? The way that you normally see this written, we don't write it as x equals negative 3. When we have function notation, usually what we write is this: f of 3. We say take the x out and put a 3 in. So you would get f of 3 is equal to 6 times, I guess I'll do it, negative 3 minus 2, and then f of negative 3 is equal to negative 20. And then sometimes students do something really catastrophic. They divide both sides by negative 3 just so they can solve for f. That's not what you're doing here. This is just notation. It's just notation. You're not solving for f. This is your y, actually. So this is your y. It's not an f. It's not a negative 3. This is just an alternative way of writing the y value when x is negative 3. So your y value is negative 20 when your x value is negative 3. Okay? So let's go ahead and do it the way that we're supposed to. So f of negative 3. So once again, I'm going to substitute negative 3 anywhere I see an x. So plus 3 times negative 3 plus 3. These are wild in this problem, I guess. So one of the errors that I see a lot from students is they go, oh, negative and negative is positive. Nope. PEMDAS says you deal with this exponent first, then you deal with this negative on the outside. So this result will be negative 9 minus 9 plus 3. So this is going to be negative 15, because negative 18 plus 3 is negative 15. So when the x value is negative 3 in this function, the y value is negative 15. And students freak out with this one. They're like, well, what do I do with this t? It's the same thing you did over here. You replace all of the x's with this t, so you end up getting f of t is equal to negative t squared plus 3t plus 3, and then we move on to the next problem. There's nothing that you can do with that. All right, so let's do this one. So g of t plus 2 is equal to, again, take your x out and put this t plus 2 in. So t plus 2 plus 1. So start to simplify. Plus 10 plus 1 is equal to 5t plus 11. And that is what g of t plus 2 is. Okay. The reason why we use different letters here, we were using f, now we're using g, is to just represent different functions. Okay. I had mentioned earlier, I said there's lots of different ways of why we use function notations, and that is one of the reasons why we do it. Is we want to be able to represent these in a different way. Two different equations, two different functions. One is f and the other one is g, and we will know exactly which one we're talking about. Okay, so over here, find f of 2. So again, when your x value is 2, what is your y value? And f of 2 is 1. Okay. So let's write an equation in function notation. So this is what we have right now, and we want to write this in function notation. In order to do that, you want to get y by itself, so that way you can take your y out and put your f of x in. Okay, so I'm going to subtract x squared to both sides. So that gives you negative 4y is equal to negative x squared plus 3. And then I'm going to divide by negative 4. Divide by negative 4 to everything. And that gives you y is equal to 1/4 x squared plus 3/4. And now we can write it in function notation. F of x is equal to 1/4 x squared plus 3/4. Okay. Give the function and its domain. So again, you look at this and you're like, well, how am I supposed to do that? Well, remember, this is just a y. Y is equal to negative 1.5, which is a horizontal line at negative 1.5. So I'm going to put my horizontal line in, again, as close as I can get it as possible. There it is. And giving the domain and the range should be a snap, because the domain here, there's no restriction on x, right? It's just going to keep going left and right. So my domain is negative infinity to positive infinity. And my range is pretty basic. It's only one number. There's only one value here in this entire graph. My range is simply negative 1.5, and that's it. All right, so that is going to be it for this video in chapter 2. I will be posting the chapter 3 video sometime this week. So thanks for tuning in.